So the last two classes, we kind of introduced the broad notion of function as an input-output system. Every input has a unique output, and we've kind of sketched graphs of different kinds of functions. Like just generally, if you plot points and figure out an x squared graph will look like a parabola, an x cubed graph will look like a squiggle line. A root graph, and then we talked about domain and range and maximums and minimums. And we were talking very broadly about those things. And so part of this module focuses in on a couple specific kinds of functions. And so today we're going to focus on linear functions. What do you know lines have to have in order to be defined as line? So there's an independent x. X is always the independent, and y is the dependent. So for instance, x could be time, and y could be, say, liters of water, maybe. If you're filling, let's say we're filling a pond. We have a pond, it has 50 liters of water, and we're gonna pour water into it. Yeah, constant rate of change. If I was pouring water with like a very consistent rate of change into this pond, let's say it was pouring 5 liters per minute. I don't know how realistic that is. So then at 1 minute, I started at 50 liters, just estimate. And then it's gone up by 5. So now that's 55. After 1 minute, after 2 minutes, it's a constant rate of change, which is your slope, right? It goes up another 5, and then 3 minutes. So you could make a table of values where x and then y, which is actually a function of x also, you could write it as f of x, we talked about last day. At 0 minutes, we had 50. At 1 minute, we had 50 plus 5, right? At 2 minutes, we had the 50 liters plus 2 5s. At 3 minutes, we had 50 plus 5 times 3 5s, and so on. And if we see that pattern develop at t minutes, we're going to have 50 plus 5 times the number of times we have t. And so what that leads us to is that f of x in general is 50 plus 5x, or t, or whatever our input variable is. We could rewrite it as volume with respect to time is 50 plus 5t. Like that would be just a different description, but it's the same sort of thing. And does this form a linear relation? Well, yes, it has to, because it has a constant rate of change, aka slope. Your rise to run is your rate of change, and it's constant. It's not changing. It's increasing or decreasing consistently. So water filling at a consistent rate to a pool is a very nice example of a linear function as well. And that, let's just see if that fits with our y equals mx plus b, because that's something else we know about lines, is we always saw the rate times the input plus b, and b was always our y-intercept, because when you replace x with 0, you have the y-intercept here, 0, 50. Does this function follow an mx plus b format? Yes, it does. We have our slope and our y-intercept and our independent variable, which is kind of like our input. It's like time is usually independent, and then our dependent variable, which is our output. All right, so there are obviously other things we might want to know about a linear function. So we might want to know when the x is in, when the y-intercept happens, when the x-intercept happens, when the slope happens, where there's an intersection somewhere. And so, yeah, I mean, the other thing is sometimes we're given only some points and we're asked to write an equation for that, right? Like, so maybe we were given that 0, 50 is a point and that 365 is a point. And they told us nothing else. Then we'd have to think about how do we use those 2 points to find the slope and to create a line equation and then to graph it out and then to potentially predict other points like higher points or lower points. Okay, so if they gave us 0 and 50, this is a y-intercept, right? Anytime you have x being 0, that's a y-intercept. If you have y being 0, that means there's no height, so it's on the x-axis. That's an x-intercept. So, you know, if I have the equation v of t is 5t plus 50, how do I find the x-intercept? Well, I would let y be 0, or the output be 0, so that'd be 0 is 5t plus 50, and I'd figure out what t value, what time value made it 0, right? That point is somewhere here in the negatives. So if I subtract both sides, I get negative 10. So negative 10 comma 0 is my x-intercept. And if I have this and I want to find the y-intercept, and this will go for any function. It doesn't have to be a linear function. It could be a quadratic. They might ask what are the x-intercepts, which is going to be a very important question when we get into quadratics, because those are called zeros or roots. They're usually the solutions to an equation. And sometimes we're interested in y-intercepts. Usually for lines, we're more interested in y-intercepts. That's where we let x be 0, because, right, to be on the y-axis, the left and right direction is 0, and you're just looking at where it is on y. And so you're essentially looking for when is it that, like how much water is there at time 0, and that's usually pretty easy because that's usually just this b value, because that's just going to go away and you're going to get 50. So 0 comma 50 is the y-intercept. Right, so that's one question you could get asked. Another question that you could get asked is, okay, so let's say you have these 2 points, right? So at 1 minute it was 55 liters, and at 3 minutes it was 65 liters. So let's say you have 2 points, and then they want you to write a line equation. I want you to take like a minute on your own paper and think about, if you were only given these 2 points, how would you proceed to write a line equation of the line that passes through those 2 points? So slope is going to be looking at the up and down direction distance and the left and right direction distance. Now, remember, we took the difference of the y's. So rise with the y's, run from your x's. So then when you do your difference, you want to make sure you're doing it in the same direction so that you have the relationship there. And that gives us what? 10 over, oh, I wrote that down right. I wrote the answer there. Yeah. 10 over 2, which is 5. And we already knew that. But yes, like this is how we would find it if we didn't know that, right? So it's nice to confirm that that's exactly 5 was the number of liters per minute that it was increasing by. If it was decreasing, if it was draining by that much, it would be a negative, right? Because the next term would have been 45, not 65. Okay, so if it's 5, that's the same as 5 over 1. So that's like every time you go up 5, you go over 1. Or if you go down 5, you go left 1. So that's, remember that that's the same as 2 negatives. 2 negatives is the same as a positive. If you have 1 negative, that can only be in the numerator or the denominator in terms of how you read the slope. That's not the question we have though. Okay, so we found the slope, great. So that's not the question though. The question is write a line equation. So what do we do next? And this I've explained in 2 different ways in the past. Yeah, so we could find the y-intercept. At this point, we don't know what the y-intercept is because we don't have one where x is 0. If it was given to us, then we'd already know it. But essentially, you could just say, I know that it has to look like this in the end. So I'm going to plug in everything I know and then see if I can solve for what I don't know. You may have learned it by using this formula. That's perfectly fine if you do that. This is really just the slope formula. In this one, you'd fill in the point. One of these points, I could choose this one, or I could choose the other one, but not both. And the slope, and then you solve for y, or you could do this slope. And I still don't know b, but I could plug in an xy pair, such as 155, because I know 5 times this plus b has to be that. And so when I do that, I get b is 50, which then means that y is 5x plus 50. And again, this y could always be a v of x or a f of x in function notation. Okay. And then the most sort of difficult type of question you may have would be around writing a line equation that is either parallel or perpendicular to a line that is given. So let's say we had the same points. I'm just going to stick to this. But it said, write a line equation for a line either parallel or perpendicular. Let's say perpendicular. Now, to this line, passing through, and then let's say it passes through a different point, such as, I don't know, maybe it passes through 230. I don't know, just made it up. Okay, so think about, first of all, okay, line equation means we're going to have some sort of result like this, which means we need a slope and a y-intercept. We can get the slope of this line, which we know is 5, but they want a line that's perpendicular. So that is telling us about the new slope. What is the perpendicular slope? If you have 5 over 1, that's like 5 up over 1, right? So that's your sort of slope triangle. If you try to make it 90 degrees, see 1, 5 would go 1, 5 like this. So it might not be perpendicular. So you're on the right track though. We have to think, what if you rotate this line? Do you see that line? But rotating that line by 90 degrees is going to give you a perpendicular, because perpendicular is 90 degrees. Okay, so imagine that little L shape there, the 5 to 1 L, and drop it down by 90 degrees. So go like, that rotation is going to be now showing you a 90-degree relationship here. Because if you take the blue ones and you rotate them, then you're actually making these green lines be also the same relationship, the same angle relationship, which is 90 degrees. So if we think of that, that slope is down 1, right 5. So what's that? Down 1, right 5. So what happened? From 5 over 1, we got perpendicular, we got down 1 over 5. Okay, so let me ask you a different question. What if you had a regular slope of 2/3? What would its perpendicular slope be, given what we just tried here? So it's not only flipping, it's also negating, because flipping only might still not line it up. It won't line it up 90 degrees. You need to also negate it. So notice how, yeah, So it'll be negative flip. And these two, like if you multiply them together, they should always give you -1. So sometimes people define it as perpendicular slopes will multiply to -1. What if this said parallel? What's the parallel slope to 5? 5. Yeah, parallel is just the same, right? Parallel lines are just going to have the same slope, and that's it. Like you're just going to essentially be moving the line so that it passes through this point instead of those other points, but it's got the same angle, right? Whereas if you want a perpendicular slope on your picture of what we did before here, right? If we want a perpendicular line, it's going to be kind of like, maybe for it to go through 230, it would have to go kind of like that. That's the line we're trying to get. Where a parallel one would go kind of like that, right? So it just dropped down. Either way, whatever they tell you, what they're asking about is for you to write a line equation. And the write a line equation means you need a y equals mx plus b. It means you need a slope, and then you need the y-intercept of the point it passes through. So since they want us to pass through this is our x, y, and then we take the slope of whatever they asked us to, whether it was perpendicular, it's this one. If it was parallel, use the other one. So let's put that all together. We'd have y equals mx plus b. So our m was -1/5. Or b, we didn't know yet. And our x-y pair that we want on the line is 2, 3, 30. So I made it up, so it's not going to be pretty in terms of whole numbers, but that's okay. This is -2/5. If I add the 2/5, and my b is going to be 30 and 2/5, which I could make a mixed number if I wanted to. So that means it's going to be y is -1/5 x plus 30 and 2/5. I think Alex would make you want that as a mixed number. So you'd have to turn that 30 times 5 plus 2. So whatever that is, over 5. Okay. And again, if it were parallel, this slope would just stay at 5. And so, yeah, so those are types of problems you might get. These are in the video, so if you want to watch this again or watch a different video, there's more examples of writing line equations. But that's pretty much as hard as it gets, is when they don't give you a slope, they just give you 2 points. You have to find the slope, and then you have to identify a parallel or perpendicular to it. Okay, so let's just look at a few contexts where we have linear relations. So like you could be given some data points that might become linear. You could also be given a situation that ends up being linear. So like the water filling question. Here's an example where a company has 2 molds to form tires. So you're making tires, and you have 2 different possible purchases to make, one of which starts at $1,000, and then it starts costing you 15 per tire. You could call that tire, number of X is number of tires made. So then you could say f of X or Y, maybe let's use f of X to get used to it, would be the total cost for that machine. And f of X is always, because this is a dependent on the independent, the total cost is with respect to the number of tires, of course, because the cost is going to depend on how many tires you make. Right? So you could have a function for the first mold, right? Okay, what's the function for the second mold? So g of x, let's say. What's g of x? Okay, we got a contender here. It's going to be 3,000 plus 10x. This is your classic case. If you spend more money on something, typically it's going to cost you less in the long run, but you have to wait some time before it is worth it, right? So if you're going to get a new furnace in your house, you're going to get a high efficiency furnace. It's going to be way more expensive. But what is going to happen is over time you're going to have less expense, right? So there's a break-even point. If you graph these two things, you're going to notice some things, right? You have your rate of change. So your first one is 1,000 and then plus 15x, so 15 over 1 every time. I'm just approximating. And then the next one's going to start at 3,000, but then go up a little bit slower. So eventually what happens is you're going to have a break-even point at a certain number of tires where these meet, and this is kind of like a systems of equations where you would equal this to that, you would solve it and you'd find out how many tires it would cost for the more expensive one to start being less expensive, right, overall. So that functions can be useful that way to identify that. You could graph and then find the intercept and go from there. So there's this other example here that you might find a little bit interesting. Okay, so yeah, I mean, here, this is really short.
How about Rich and the 40? So here we go again. Rich, miles per hour with strides. That's going to be the first thing you see. Let's check you out. Go. What are we looking at here? What are we topping out? 16.0. All right, here we have Rich versus Julio Jones, full speed. Rich, you got to stay in the picture. All right, how about with a 10-yard lead? And here comes Julio. Okay, now versus Julio, half speed.
No, not half speed.
Okay, so is this a rate of change type question? Yes, it is. Funny, right? So they're taking Julio half speed compared to Rich regular speed. And so what happens after we go through all these things here, they give us a table of values. So this is Julio half speed, number of yards per second. And you can just already imagine that there is a rate of change here that is consistent, and we're assuming linearity, and so is there one for Rich as well. And so maybe just look at the data here that you see on the screen, and what is the rate of change for Rich, and what is the rate of change for Julio? So what are the slopes? Okay, so what are you noticing? What's the rate of change for Rich? These are nicely consistent, up by 1 all the time. 6.2, so it's going up by 6.2 each time, right? So for every second, he's going 6.2 yards more. Okay, anyone get Julio's half speed amount? Is it consistent? 4.8? Yeah, and you could subtract to figure that out. And pretty much what we're doing is we're calculating slope, because it's as if we've been given, Julio had points like 1, 4.8 was a point, and then 3, 14.4 was a point, right? And then for Rich, you had 2.07. And when you do that, and you subtract your y's, and then because your x's are 1, you're going to get 6.2 as the sort of slope times the number of seconds, and then probably plus or minus some sort of b value. We don't really know what that is. I think he stopped and came back later, like, right? He kind of started later, and then Julio was starting already because he was half speed. But you could create a line equation for Rich, you could create a line equation for Julio, and you could figure out, like, when are they going to catch up, right? If one kind of started later and one started right away. When are they going to catch up? So there's that kind of question. Obviously, if we don't know this, you could just throw in a point. You could throw in, okay, at 2 seconds, it's 2.07, and you could use the y equals mx plus b to your advantage to figure out what b is. It's going to be some negative 2.07 minus 12.4. So it's negative 10.33, I think. So the equation for this would be y equals 6.2 x minus 10.33. And again, you can talk about what does it mean in this scenario to be an x-intercept? What does it mean to be a y-intercept? The y-intercept doesn't really exist because it's like negative distance. It's not like, it's just the fact that he was waiting around and then he went. So the x-intercept is really kind of telling you when he started. So I think it was the 2 second or 1 second delay here, right? So yeah, we won't do Julio's equation, but you can see that these are linear functions that you are using to describe and model real life situations. So right, here's one from your textbook. You have this data given. So this one's a little more serious than the other one, of the revolving consumer credit, of the amount of credit used by all of the US, I believe. So in 2003, it was 791. 2004 was, in billions of dollars. And so we won't do this one completely, but, how do you start it? Well, you can kind of sketch out your points. You see that, yeah, they're increasing. You could put dates on here. And maybe they're not exactly linear, but I think they're going to tailor them, because it's a textbook, to an approximate sort of linear model. So they're asking you to create a linear model to predict when the consumer credit will exceed 1.1 trillion. So, you'd want to figure out what the slope is. So because this is in units, you'd want to look at these differences, maybe average out the differences so that you have sort of an average slope, how much it's increasing per year. And then you can use your y equals mx plus b to ask the question of when will it reach 1.1 trillion in terms of, that would be your y value, right, for your x and y.